So welcome back to Physics of Music. In this video, I'm going to review the similarities between light and sound, and then ask the question whether there's a light analog of a musical instrument. And then in the next video, that's actually going to lead us to an understanding of one of the most important and fundamental pieces of physics in our universe, and that is the subject of quantum mechanics. So to remind you, what we understood in the last video is that light fundamentally is an electromagnetic phenomenon. If you have light from a flashlight, then you could ask, what is that? And there's a deeper understanding that we've had since the work of Maxwell in the 1800s. And that is that the light is actually related to oscillations in the electric and magnetic fields. And I've indicated that here. So if you were to go in and freeze time at a moment when there's light coming out of this flashlight, and if you somehow had a way to measure these invisible electric and magnetic fields at this instant in time, then you would see a picture like this. Along this line, you would find that the electric field varies in its magnitude and its direction, and similarly the magnetic field varies, and the pattern for light with a particular color, or one of the colors of the rainbow in particular, the pattern would look very much like a sinusoidal wave. And so we can characterize this sinusoidal wave in the same way that we characterized sound waves. We can assign an amplitude to it. That is the maximum magnitude of the electric field in the wave. There's a wave speed. So as this light is moving, this entire pattern of electric and magnetic fields moves to the right with a specific velocity that's much greater than the speed of sound. It's around 3 × 10⁸ meters per second. We can also assign a wavelength, and that is just the distance between these 2 points where the electric field is maximum in some direction. And finally, we can assign a frequency to the wave, which is if I go to a particular point, and if I were able to look at how the electric field is varying with time at that particular point, it would be oscillating back and forth. And so the frequency of our wave is just the frequency of that oscillation. And just like for sound waves, the frequency, the wave speed, and the wavelength are related by this basic formula. And we understood how these wave properties were related to our perceived properties of light. The amplitude of wave, if we vary the amplitude, it's going to change our perceived brightness for that light. The wavelength, if we vary that, then that's going to change the color of the light that we perceive. And so we talked about last time how in this particular range of wavelengths from 0.0004 millimeters to 0.0007 millimeters, those are the wavelengths of electromagnetic waves that we actually perceive as light. And varying the wavelength in that range will change the color that we perceive, going from violet for the short wavelengths to red for the longer wavelengths. These wavelengths correspond to frequencies that are much higher than the frequencies that we discussed for sound waves. But we can also have electromagnetic waves which have wavelengths and frequencies outside of this range. So for example, ultraviolet light or infrared light, or microwaves or radio waves, or X-rays or gamma rays. So these are all things that physically are just the same as light. It's just that you have a different range of wavelengths, and for those wavelengths, our eyes are not designed to perceive those. And so just like sound, if you consider general sources of light, then the superposition principle applies. We can think of these general sources of light as superpositions or combinations of light waves with specific wavelengths or specific frequencies. So in the case of sound, this was the idea that any sound can be built up from pure tones with specific frequencies. When we're talking about light, the analog of a pure tone is what we'd call a monochromatic wave, so a single color of the rainbow. And we can represent then a general light source. We can think of it as a combination of these monochromatic waves. And so again, just like for sound, we could represent the content of a particular light source in terms of its monochromatic waves by a spectrum graph. And this just shows us for each possible frequency of light, or for each possible wavelength, how much do you have in your source of light. So how much light is there in the range that we would perceive as red or yellow or blue or purple. Okay, so this is an example of the spectrum graph for sunlight at the surface of the Earth. And you see actually the spectrum extends outside of the visible range, so there's a lot of light or magnetic radiation, which is in the infrared range of wavelengths that we can't see, but we can feel as heat. And then there's other infrared radiation from the sun, which is in the ultraviolet range that again, we can't see, but it can cause sunburns. Okay. So the question that I want to ask in this remaining part of the video is there some analog of a musical tone for light? So remember, we talked about how if you look at the spectrum of a general sound, like a noise, then it tends to have components at all different frequencies or many different frequencies. So this is a recording that I made of crumpling up a piece of paper. I made that in Audacity, and then I plotted the spectrum, and this is what comes out. And so you see that over this very large range of wavelengths, we have, or frequencies, we have lots of contributions. Whereas if you have a musical instrument, that produces a very, very distinctive spectrum graph where you have mainly sounds coming from in very specific frequencies. So for musical instruments that produce definite musical tones, then you have a fundamental frequency and then sound at various multiples of that fundamental frequency. So this is an example that I made with a recorder. This is another example that I made with a harmonica. Okay, and you can see then these musical tones are very distinctive compared to just the spectrum from a general sound. Even if you have something like a drum head and you tap that, then that also would have a set of peaks. They just wouldn't lie in this simple harmonic series. Okay, so these musical instruments are producing very, very characteristic spectra. And we can ask, is there something like that for light? Is there anything that would produce light that has a spectrum that looks something like these musical instruments? And so the answer turns out to be yes. So if you look at the spectrum of sunlight, like the one I showed in the previous slide, then that looks kind of reminiscent of the spectrum for general noise or the crumpling paper that I had. So you have all sorts of different wavelengths there. You get a similar spectrum if you just look at basically any kind of object and maybe you heat up the object so it's red hot and you look at the spectrum from that. So for example, a light bulb filament in an incandescent light that's very, very hot, it's producing lots of light. If you look at the spectrum of that light, it looks pretty much similar to this, that it's light with wavelengths that are continuously distributed over the whole range of visible frequencies or visible wavelengths. Okay. But there are sources of light, it turns out, that look a lot more like the spectrum from these musical instruments. And it turns out that what you need to do is look at basically the simplest possible materials or the simplest possible form of matter and look at the light that produces when you heat it up. And so the simplest possible form of matter is where you just take a bunch of atoms of one type, for example, like hydrogen atoms or helium atoms, so pure atoms, and you have a gas of those. So they're not even interacting with each other. They're not condensed into a liquid or a solid. They're just basically freely moving around, doing their own thing. And now you add energy to that system so that now you have a hot gas of pure hydrogen or of pure helium. And so if it's hot enough, it will emit some light, and you can figure out what the spectrum looks like. And I've shown the example here for pure hydrogen and for pure helium. And so you see that those have very specific frequencies of light that are present, and it's different for hydrogen and different for helium. And you can do this for any element. And so some of them will have a simpler spectrum and others will have a more complicated spectrum, but they are characterized by having light at these very specific wavelengths. So I just wanted to make sure that you're understanding what these graphs are showing. And so I want to remind you how you might figure out one of these graphs. So what I've got in the left picture here is some hot hydrogen gas in a tube. So this is a tube with that electrically can excite the atoms, can add energy to the atoms in this tube. And you see that it's glowing this particular pinky purple color. And so now what you could do is take the light from that tube, send it through a prism, and then that would split it up into its various wavelengths. So if that were sunlight, this would look like a rainbow. But with the light from pure hydrogen atoms, then it just has a very funny rainbow, which only includes light at this wavelength in the red, this wavelength that's kind of cyan, and then a couple of wavelengths over in the violet range of the spectrum. And so if we plot the amount, say the amount of energy in each of those different lines, we call them spectral lines, then you get a graph like that. And so that's what this spectrum graph means. So our question is, why do these pure atom systems, why do these simple systems produce spectra that look like musical instruments? Why are atoms like the musical instruments of light? So I'm going to end this video just with that question. And it's interesting to contemplate this and see if you could come up with any ideas. And so what I want you to think about is, from our previous discussions, what is it that explains why a guitar string or a trumpet produces a spectrum that has these sounds at very specific frequencies? And you can think about, could that same explanation apply somehow to atoms? So I'll talk about the resolution of this in the next video, and that will actually end up getting us to the subject of quantum mechanics.